put it in the binder. Ready to go. So here's a second lecture on direct detection.
All right, so we'll get started right away. So if you remember yesterday, we had talked about scattering rates primarily. We're going to start today by finishing up our discussion of scattering rate, because what we didn't get a chance to talk about is the fact that there is actually a way that you could see a distinguished signal in dark matter detectors based on essentially the motion of the Earth going through our solar system. So we'll talk about that just briefly to start with, and then we're going to move into talking about backgrounds. So backgrounds are something that are really important for direct detection experiments, like understanding your backgrounds. And I think some of you may be very surprised at the lengths we go to essentially inventory and characterize these backgrounds. And so I want to at least get you an appreciation for the amount of care that goes into constructing these detectors. And then I think this morning's lecture, we'll talk a little bit about some of the experiments and maybe start addressing the question like, is it possible that we've already seen a dark matter signal? And then my hope is that that will stop and it will be 12:28 when we finish that discussion. And then this evening, since we have been having a lot of discussion throughout the lectures, I'm going to take this evening's time to sort of finish the lectures and continue the discussions as we've been going, rather than having a dedicated discussion period. And so this evening then, we'll start by talking about liquid noble experiments. We'll talk a little bit about bubble chambers, how they work and how they can see dark matter. And then we'll talk a bit more about the solid state cryogenic detectors, the technologies and some of the science behind them, and then wrap up with some sort of futuristic ideas of the directions that some of these detectors are going and where we're kind of going with WIMP space. So primarily we talk about traditional WIMPs, but at the very end, I'd like to talk a little bit about perhaps sort of non-traditional WIMPs that are sort of lighter than a GeV, and how it is that we now have detector technologies that are capable of saying something about that, or at least going in that direction, where hopefully we'll soon have a lot of reach there as well. Okay, so let's get started. Okay, so so far we're sort of right at the end of here, so it looks like we have a lot to cover, but I suspect that some of the stuff might go a little faster, or maybe I'm just way too ambitious. All right, so we talked a lot about the signal last time and the signal rate. And remember, I told you, we're seeing this recoil spectrum, and there's just nothing about that recoil spectrum that sort of could distinguish perhaps your signal from a background. But it turns out that there are some distinguishing characteristics that you could have in a dark matter signal if you constructed an experiment where you could actually be measuring a lot of dark matter interactions. So the first one is the idea is that you have this time dependence. So this is the Earth revolving around the sun. Okay, so that's one motion that you have going on. And then you have the sun moving, which is essentially our solar system, moving towards the star Cygnus. And so what this means is that essentially, if you want to think about this in a reference frame, it means that there are 2 times of the year where the Earth is moving parallel to the wind or anti-parallel, and other times that it's entering the wind at some angle. And so as you can imagine, just like if you're flying in a plane or something or riding your bike, right, your flux is bigger when you're going into the wind and is least when the wind's at your back. And so that's the idea here. So essentially, the Earth orbits around the sun. It gives what we call an annual modulation. It's a sinusoidal dependence. So the Earth speed with respect to the galactic rest frame is largest in the summer in June, when we're parallel and kind of going in the direction of the WIMP wind. And in December, we're going anti-parallel. And so as a result, we expect to have a fluctuation. If you are seeing a large signal, you would see a fluctuation in that signal. And so that's one tool that we can use to help distinguish this. Now, this is actually a very tiny fluctuation that you're trying to measure. So if I were to make a plot, so this is a log of our rate versus recoil energy versus variation in the spectrum. And if I kind of draw this as a cartoon, and I were to say, what is the rate in December and plot it in green and say that's just like going to be the rate all year long versus what is the rate in June if you were to do it all year long, you can see that this is a very tiny difference. And so if you want to use this kind of signature in detecting dark matter, you need to be seeing something on the order of like 1,000 events in order to make a measurement. And so, so this is essentially giving you the ratio of the orbital speed of the Earth versus the sun's circular speed. So you can, since this is such a small number, you can tailor expand. And so this is where you get your cosine modulation term if it is that you want to predict what these signals would look like. And so clearly you have a phase and you have a period that would come into this as you would expect with any kind of cosine function. So that's essentially it. And this is the technique that Dama Libra uses in order to try to detect dark matter. There's a second signal that you can get from sort of a modulation, if you will. And this actually has to do with the fact that the Earth spins. Okay, so again, okay, so here I have the sun, I have the Earth going around the sun, and just for reference, this is the sun, you know, moving through, or our solar system, I guess, moving through the galaxy towards the star Cygnus. And in here, I've blown up the Earth, okay? And so this is the North Pole. The Earth spins about its axis. And the idea here is that if I put a detector on the Earth, at different times during the day, the orientation of the detector with respect to the wind is different. So what you want to do in this case is you want to be able to track, right, the recoil going through your detector, much like you would think of a collider tracking in a particle, but the tracks here are really tiny. Okay, so you want to get a direction that the particle is going in. And if you have particles that are, you essentially reject all the particles that don't come from the direction of the WIMP wind, and everything that comes from the WIMP wind would be your dark matter signal, your WIMP signal. And so there are experiments that do this as well. So this next slide here just kind of, again, gives you sort of the equations. If you went through and did the math, you know, how it is that you would, what the things you would take into account. So here you have to know the Earth's velocity parallel to the direction of the solar motion. And then what you need to measure is this angle here. So it's the angle between the solar motion and the nuclear recoil. Yes.
So I guess there's an assumption here with the WIMP wind that the WIMPs are moving along their geodesics.
Okay, so I mean, like, okay, I'm not sure exactly what you mean by WIMP geodesics, but essentially this is what I would say. Like in general, like, you know, the WIMPs really kind of do move in a random way, right? This is like a gas that you would treat, you know, as some kind of distribution. But the idea is that you know, take an average, like on average, this is what you're doing. And then, you know, the reference frame, the fact is that the Earth is moving. So if you take it to be still, like the WIMPs to be still, the wind is coming from the motion of our planet moving through.
I see. Thank you.
Okay. Yeah, and
yes, essentially the assumption is that the dark matter halo was not correlating with the galacticness.
Okay.
So dark matter halo was more or less just repeating as rotating very slowly. Galacticness is going much faster.
okay. Is that what you meant by geodesics? Okay, I was like, I hadn't ever heard anybody talk about wind geodesics before, so that, sorry if I misunderstood.
I have a
Yeah.
question. But do you have ways to constrain the wind motion around the galaxy? Like, how do you know that the wind is not spinning in the same velocity?
If the WIMP is spinning at the same velocity as the Earth,
Yes.
I don't think this works. I wouldn't see how it could.
Yeah.
In the same direction with the same velocity, like I'm not sure that you would ever be able to measure something.
The reason for thinking that it's not is, I guess, based on, I mean, anecdotes or expert on this than I am, but it's from simulations, and I guess just from the general principles of like angular momentum conservation, the ordinary matter has spun down into this contracted disk, and so it's spinning a lot faster than the dark matter halo, which is still like the.
So I guess I need to repeat what Tracy said is like, there is a good reason, or at least a reason, that you might consider that the WIMPs are not rotating at the exact same time as the galaxy, and that being that the ordinary matter has, via conservation of angular momentum, the ordinary matter has spun down and then, is moving at a different speed than the WIMPs.
But ordinary matter is a disk.
Yeah,
That's
as
kind
a
of the
disk,
big
yeah,
deal.
the disk, and the ordinary matter, of course, being the disk.
But the better answer is probably that we've done detailed simulations of dark matter
Yeah.
flows. Like, that's where the prediction is coming from.
Yeah.
We don't have a direct observation of constraint on how fast the dark matter is.
So there's not a direct constraint on how fast the dark matter is going, but we do have lots of simulations that indicate that this is a reasonable assumption. But you're right. I mean, if it turns out that we're all wrong, then again, why we should have more techniques. All right, and let's see. Okay. So with that, so talking about signatures, dark matter signatures, we're done. We're now going to move on to backgrounds. All right, so there are a lot of sources of backgrounds that we're concerned about as experimentalists when we're designing our experiments and when we're building them, constructing them, deploying them. The first one that I'm going to list is environmental radioactivity. So this includes radon and its daughters. And it's probably one of the sort of environmental factors that we worry about the most when it comes to radio impurities. The second thing is that the materials that you construct your detector from are actually radio impure. So we care about the radio impurities of the materials that we use for the detector construction. And as you know from our lecture yesterday, like a banana is radioactive in our minds. These are very, very small measurements that we're worried about. We also worry about radiogenic neutrons with energies below 10 MeV. And the reason is that neutrons in these detectors look identical to WIMPs for the most part. And so they're very concerning. They can be very concerning. And so we worry about neutrons that come from alpha N interactions and also fission reactions. We worry about cosmic rays and their secondaries. We worry about activation of the detector when it's near the Earth's surface. So like if your detector, for example, is a crystal, like germanium, it actually gets activated just from cosmic rays, essentially, while it's on the Earth's surface. So while you're working and putting your sensors on it, your detector is becoming activated. Yes.
Why do we only care about radiogenic neutrons with energies below 10 eV?
So if the energy is very high, it will produce like recoils that are very high, and it will be outside the region of interest.
Okay.
So we worry about anything that will produce a nuclear recoil in our region of interest. So essentially the region, and generally this is anything below, say, 100 keV in nuclear recoil. So if it can produce that, then we worry about it. And then, of course, these are sort of the categories that we've identified. Every time that we're building in a new regime and we're thinking of something else, something new comes up. Like the idea that your silicon can be contaminated with stuff. I mean, it was something we didn't even know until Damit had made some measurements and saw backgrounds in silicon that actually came from cosmic rays striking the argon in the atmosphere, and then the silicate sort of sand that they make the detectors out is where the contamination is starting. So like, things we had never even thought about. All right, so I want to take just a brief aside here because I think that radioactivity is something that a lot of times as graduate students, we don't really think about. So I just want to review quite quickly the radioactive decay equations that are useful. So we care about activity. So this is decays per unit time. It's measured by the decay rate of a radionuclide. So that's A, it's the number of radioactive atoms divided by time, and it is characterized with a decay constant. The decay constant is the probability that the radioactive atom will decay, and it's given by this formula. And then the number of atoms of the radioisotope present is given by Avogadro's number divided by the atomic mass of the radionuclide times the mass of the radionuclide. And then finally, the other thing that we talk about often when we're talking about backgrounds and we're talking about our materials, we talk about the abundance. And what this refers to is the relative portions of the stable isotopes of the element. And so just a brief reminder of some of the vocabulary that you might hear. All right, so one of our lines of defense against these backgrounds is the event signatures. And when we're looking for a traditional WIMP, this is fantastic, right? We can get rid of a lot of backgrounds that remain just by the event signature. And basically the idea is that if you have a particle that comes in, that's like a photon or electron, which is primarily the majority of your background, it will strike an electron in your crystal structure and produce an electron recoil. Where WIMPs and neutrons, they will scatter off the atomic nucleus. And most experiments, and so basically, when those interactions happen, energy is deposited into your detector. And depending on what type of detector you construct, you're going to see energy in sort of three different ways. You're either going to see phonons, or you might, if you have a crystal or a target that scintillates, you could get a scintillation signal, or you could get an ionization signal out of it. And so there are lots of experiments. There's also the superheated crystals. So phonons and superheated crystals, in some sense, these types of detectors are measuring heat in some way. So that's why I kind of put this up over here. And there are lots of experiments that actually use two of these. So for example, CREST is an experiment that measures both phonons and scintillation. There's a number of dark matter experiments that take advantage of scintillation and ionization. So Xenon, LZ, Panda X, CDMS and Edelweiss measure both the phonons and the ionization. And one of the things I just want to kind of point out here is that not all energy is equal in these ways, in the sense that if you're measuring scintillation, you get something on the order of 10 photons per keV. Where if you're measuring ionization, you get like 100 quanta. So that when I say quanta, I kind of mean electron hole pairs per keV of energy deposited. And you get something like 10,000 phonons per keV of energy that's deposited. So the signal that you're looking for can be different, via energy, depending on what mechanism you're looking at. So the reason that we really like these experiments that can measure two different energy types of energy is because there's this factor called the quenching factor. And what the quenching factor is essentially a ratio of the energy from a nuclear recoil event divided by the energy from an electron recoil event. Okay, and so most neutrons and WIMPs are nuclear recoils, as we pointed out, where electrons and photons they produce electron recoils, and your detector response is different to these two different interactions. And so essentially the quenching factor is how you relate these two different signals together. And you characterize what this factor would look like by using calibration sources. So calibration sources that produce either gammas or neutrons in order to distinguish each one. And so essentially this is, I like this cartoon because it shows essentially in three different ways of measuring either charge and photons. So this would be like if you had a xenon detector and it's very generic. If you had a germanium detector, charge and phonons. And this here is calcium tungstite. I forget what O4 is. Oxide? Oxtate?
It's oxtate.
Yes, okay. So these are measuring photons and phonons. And what you can see is, so in this thing, this is essentially your quenching factor. We call it the yield. is generally the ionization energy divided by the electron, energy divided by the recoiling energy. And so here, and this is versus then the recoil energy. And so here in xenon, these here dark dots represent electron recoils from a calibration source. These lighter colored dots are the nuclear recoils from a calibration source.
How do detectors see phonons?
Okay, so I'm going to get to that.
Okay.
Can we hold that question? Okay. It actually might not be till later this afternoon though. But absolutely, I'm gonna talk about that. Charge. This is again your electron recoils in blue. In green here are your nuclear recoils, and down here your electron recoils versus your nuclear recoils. So you can see that can provide really great discrimination. And so essentially, as an example, the visible energy is essentially 1/3 the recoil energy in nuclear recoil in germanium. So this is like a quenching factor where this is like 1 and this is like 0.3. Now, the other one that I want to talk about is bubble chambers. They're a little bit different, but they also have discrimination. So their discrimination here, essentially we have is the amount of energy posited per like unit length. So this is keV per micrometer versus energy. And what you can see is that different types of particles, right, have different characteristics in how their energy is deposited in a superheated chamber. So a bubble chamber is basically a superheated fluid that's in a metastable state. Particles interact and deposit energy greater than some threshold. And then this has to do with a critical radius bubble. And we're going to talk later this afternoon through the physics of these bubble chambers. So if you have questions about what a critical radius is. But basically the idea is that when a particle interacts in a bubble chamber, if it deposits enough energy in a certain amount of time, it creates a bubble or within a certain radius. And the basic idea here is that I can tune my detector to be insensitive to my backgrounds. So if I set my detector at 15 PSI, that's sort of here and here, any particles in this white background or this white region do not form bubbles. And so, I can crank that up to 65 PSI and remove more, right? So essentially the idea is that I can tune my chamber to see the particles I want to see for the most part and reject the particles I don't. And that's what that last bullet said. And then, once you do this, essentially it's, a cut and count analysis. So it's essentially what we've done in the past. Nowadays, the cut and count analysis is not sufficient. And so we started moving to a lot more sophisticated techniques like using profile likelihoods and other types of multivariate techniques. And those techniques rely on us putting background estimations into them in order to reach the most, the best sensitivities, to lower our sensitivities. And so again, even with this really great discrimination we have, there's still backgrounds that leak in, and we still want to characterize them and get the most out of our analysis tools. And so we do that by characterizing the backgrounds and using these multivariate techniques. So moving on to more backgrounds. So cosmic ray. I like starting with cosmic ray backgrounds as the first to explain because they're like the easiest to get rid of in the sense is that all you do is you put your detector underground. The deeper you put it underground, the better you protect yourself from cosmic rays. So that means that our students don't get to go to CERN and sip cappuccinos, but they get to go to these great underground mines with no sunshine in wonderful locations where there's snow and no light. I'm really selling this one, but essentially the hadronic component of these cosmic rays can just be reduced by actually I have this. It's supposed to be MWE. I see a typo here. So this unit called meters water equivalent. Let me explain this for somebody who hasn't heard this before, because when I was in graduate school, people said this all the time. I had no idea what it meant until I asked and someone explained it. But essentially, if you think about the overburden in different locations, it may be that some types of rock or overburden are better at, say, absorbing the cosmic rays than other types. And so to do fair comparisons between different locations, you take the overburden and you convert it to what if it were a meter water equivalent, what would it say stopping power be? So meters water equivalent and so like I said, we go to these places. So currently there's about 17 underground sites for doing physics research in the world, and they all have a little dot here. And so the reason that you want to do this, you can see starting at WIC, which is in the United States, going to Snow Lab, and Zheping in China is even deeper. You can see how it reduces your total muon flux from cosmic rays by going deeper. So what we do, the processes that we worry about, even with the muon flux, is that you still can get neutrons coming from these cosmic rays. And the processes that produce sort of the fast neutrons that we're most worried about are negative muon capture, photonuclear reactions, and any of the associated electromagnetic showers that come from your primary cosmic ray, deep inelastic muon nucleus scatters, and then, of course, hadronic interactions of nucleons like pions, muons. And so, but going deep really greatly reduces this. Yes.
Rock can be radioactive. So people take that into account.
So, yeah, so that's wonderful. So I'm not sure, is that the next slide? But yes. Oh, yeah. So the question was, rock is radioactive. So what does that mean? This is certainly something that we care about. And so rock, the underground location, okay, rocks have uranium and thorium in great abundance. So I'm actually going to address that in a couple more slides. But yes, indeed, that is something that we worry about. But that's radioactivity from uranium and thorium that's coming, not the source of that radioactivity is not the cosmic rays.
So this what's called Easter's water equivalent is just like a conversion from the depth of the overburden. Like how much
Right.
into water.
Yeah, so like say 800 meters of rock could be 1200 meters of water equivalent, depending on what that rock is, or maybe it could be, you know, I don't know, 600 meters or something, right? Like water equivalent. It just depends on what the composition is. Yes.
So what is the conversion criteria? Is it like the drop in cosmic flux or?
Yeah, I mean, so what you do is you take, so the question is, what's the conversion criteria? Okay, so when we're talking about meters water equivalent, essentially what it is that, so imagine that your detector is at the bottom of the ocean, okay? And you can do like a JANT simulation, a JANT4 simulation of if a cosmic ray comes and hits that water and there's, I don't know, so many hundreds of meters of water before it gets to your detector. And so now if my detector is, let's say at some other location and the overhead burden is primarily greenstone, or it's so much greenstone and it's so much limestone, right? So essentially then if you were to do your JANT simulation of that, right, it's not really fair. So you take those materials and convert them and say, if it was that I had that many, how many meters of water does it take to get the same flux at your detector, pretending that that overburden was water and not rock? Does that make sense? So the conversion is different depending on what the composition of the rock that's above your experiment.
Right. So it's going to be like, I guess, the overall cosmic flux because
Yeah.
different
Yeah, it's the
materials-
cosmic flux that you start with. I mean, you always start with the same cosmic flux when you do this kind of simulation. And then it's mapping the cosmic flux that you see at your detector, if your detector had the overburden that it really has, versus start with the same cosmic ray flux and stop with the same amount of particles in your detector. How much water do you have to put in between?
Right.
That's the conversion.
That's it.
Okay. Yes.
So that part is simulation, or do they actually simulate and then they put some
Yeah, so this is like simulations, right? So simulations give this to you, but they are validated. All of these sites have experiments that are there that can say, yes, the simulation, makes sense. But if you were to do your simulation in real life, like we convert it to water to do site comparisons. But if you do it in real life, you use the actual composition of the overburden that you have. So like in real life, like in Super CDMS, our simulation of the cosmic rays has like norite rock, which is the composition that's above Snow Lab. But when Snow Lab wants to compare themselves to the Dussel site or the Sussel site, right? Then they go to meters water equivalent because it's a more fair comparison of how much reduction in cosmic ray flux you can get. Does that make sense?
It's possible to reach a minimal, like a zero total flux. Like how much deep you would to get? Or
So
you
let's see.
always
So the
have-
question is there a cosmic ray that can go all the way through the Earth? High enough energy, Marco. You might know this better than me.
Yeah, I guess.
I
That's my problem.
I have never like tried to simulate to see if that's even possible. I mean, at the depths that we have now access to, you always have some flux,
I see.
but you can see that it gets much lower and lower. I don't know what it would mean to get to zero or how to simulate that. I guess you would take the highest energy cosmic ray primary you could possibly get and try to see.
Neutrinos can cross the Earth and then produce a new one on the other side.
Yeah, that's true. Yeah.
Going to field.
Yeah. So probably it's that you never get away with it, but you get
for the northern side also.
Huh?
So you can get background for the not like
from, yeah, I mean, you can,
back
yeah,
here.
but most of the background is coming from the top. I think the background coming from the bottom, that's something we don't simulate. I don't know of any experiment that simulates it so much. Worrying about cosmic rays coming from the bottom, worrying about uranium, thorium, and other things in the rock, yes. So basically, this is like swatting at flies. You take whatever is most irritating and highest, and you spot that one down, and then another one comes up, and you're like, no. So you just keep beating it down, because unfortunately, like in a non-simulated world, right? Like something is always there. So let me talk next about activation of materials, but I do promise you I am going to get to other environmental backgrounds as well. So if you have your detector near the surface of the Earth, you can actually get activation. So you can produce radioactivity in your detector material by just transporting it or fabricating it at the surface of the Earth, because cosmic rays, are coming down. So the cosmic ray spectrum, as you know, varies with height, right? With latitude and longitude, or I guess height isn't longitude. Longitude, latitude, height. So essentially, this is something to think about. So the cross section for the production of isotopes. One of the things that you have to know about this is that not all of them are measured, so that can be problematic as well. The production here of these are primarily, when we're talking about essentially this activation, the production is dominated by neutrons interactions and proton interactions, but obviously neutron interactions are the dominant here in 95% of the cases. And so this is just a table, and I think it's in my lecture notes, so you don't have to write it all down, but it essentially is telling you what the isotope is, what it decays to that is problematic, the half-life, so whether or not you can wait it away after it gets activated, your material gets activated, and then the energy of essentially the background particle that's coming out of this process, and then the activity. Yes.
What is EC in this table? The decay product?
Electron capture.
Oh, okay.
No problem. So I had to find it on the table. Any other questions? So this is something. So one of the things, the example I like to use to explain this electron capture. So germanium, which is what we use in super CDMS, gets excited into an excited state by cosmic radiation. So for super CDMS, the crystals are grown in Europe, in Belgium. And so essentially they're grown, they're pulled, and immediately after, they're grown, they're transported underground to a site called Hades. So an underground storage facility. Then, yeah, I know, it's Belgium. So then what happens is that when we're ready, we actually ship them from Belgium to Savannah, Georgia. And we use the Majorana demonstrator model, has a lead line transport box, which is bigger than me, it's like huge. And so these detectors are put in there and they're transported to Savannah, Georgia in a lead lined container. In Savannah, Georgia, they go through customs and they're put on a truck. And then they're driven from Savannah, Georgia, south of the Rocky Mountains, and then up to Palo Alto, to the Stanford nanofabrication facility, where they're again put underground until they're ready to be cut into detectors and fabricated. Now, the reason that we go that way is because even though it's a little bit longer of a drive as far as a day, going over the Rocky Mountains causes more problems. But all of this stuff we had to measure out. How long does it sit in customs? How long does the truck take to drive? Where do these go? And so, like I said, immediately we're always putting everything underground as soon as possible to stop this activation. So it was literally somebody's job to map out the logistics of moving germanium crystal. Would you like this to be your job? Look at you, become a physicist. To Texas. So now on to your question. I'm sorry I didn't know your name, but environmental backgrounds. So these are all located in mines, as was pointed out. They're deep underground. There's rock caverns all around it. So high levels of uranium and thorium in the environment that the detectors are anyway. So what do we do here? Here what we do is we use a combination of high Z and low Z materials to help diminish fluxes of neutrons and gamma rays. And so the typical materials to do that are lead, polyethylene, and copper. And so essentially, there are chapters in graduate student theses that decide like what the layers should be, what order they should be in, and how thick each layer should be in the space that's available. So it's actually a big thing. Then the next thing that we do is, in addition to that kind of shielding, we also add a nitrogen purge. And so essentially by flowing nitrogen gas, which is usually a boil off from liquid nitrogen, it's rather radio pure, and you flow it into your shielding in the empty spaces to purge out the environment itself, like the air that has higher levels of uranium and thorium decayed products. Another thing that some experiments employ, xenon one time and Lux in particular, use these large water shields. And this is basically can also help to reduce environmental radioactivity and muon-induced neutrons. And so typically, if you wanted to get like a flux reduction of, like, say, a factor of 10 to the minus 6, you need something like 1 to 3 meters of water shielding. And then the other thing that some experiments use or are talking about employing in future generations are active muon vetoes. So these are would be active vetoes, so that when a muon, say, passes through your detector, it maybe hits the muon veto first, and then you can remove any events in your detector in coincidence with the veto. And so there are a variety of ways that you can do that with dope scintillators. Boric Xeno, for example, was an experiment that was very good at this.
Have there been any space-based detectors proposed? Obviously, the cosmic rays, I guess, would be worth.
Not for direct detection.
Okay.
So I think Tracy will talk later this week about the space-based detectors that do indirect detection, but not direct detection. All right, and then just to show you, this is from a very old paper, but so this is not something that has been unknown to the community for a while. But this here in black is essentially a germanium detector that's underground with no shielding, and this is essentially the event rates that you're seeing in it versus energy. And then as you add different types of shielding, and you go add some different shielding, and here in blue, you have a lead shield and a radon purge. So you can see how just having a lead shield and a radon purge can drastically reduce these types of environmental backgrounds, just as an example. Yes.
Why does the water shield produce the background? What is happening?
Oh, I mean, essentially it's just moderating the particles.
Like how? I mean, are they interacting with them?
Yes, they're interacting in the water. And then the water can also act as a veto, like an active veto as well. Because usually you would put some PMTs in it so that you see the event signatures. So primarily the water shielding, I mean, some of it is a little bit of moderating the signal, and probably a lot of it also is the fact that it provides you an active veto as well.
Can you clarify this concept of veto?
Okay, so an active veto means that, so I have a detector, a water detector that has PMTs around it, surrounding my inner detector, which is my dark matter detector. So if I detect like a muon in my outer detector, that's water, I'm also probably going to get an event in my inner detector.
Oh.
But so if I have an event that occurs in my water detector and then in a certain time frame also in my inner detector, that event is thrown out of my data set because it's clearly from the, like, say the muon going through. The other thing that can be employed by some experiments is this idea of self-shielding. So xenon and argon, they take advantage of this. They just say, well, you know, the particles, so this is, for example, looking at a dark matter experiment. This is the LZ experiment. This is a simulation of events. Essentially, these are events that they get in their detector. And so you can see there's a lot of vents coming around the edge. These events are almost certainly coming from impurities in the wall or environmental backgrounds of some sort. So they say, well, you know what? We're just going to throw that out. Like xenon is easy to deal with. We'll just get a huge amount of it. And then what we're doing is we're just going to make a cut, and we're only going to accept events that are in this most inner portion, which is where essentially your neutrons and WIMPs can reach. But your electron backgrounds, electron recoiling backgrounds, primarily interact out here. So this is just like a liquid xenon TPC. But you know, these experiments have become even more clever and realized that they can add a skin. I think somebody yesterday had talked about this in their talk. Yeah. So essentially, you can sort of coat or put another inner detector layer inside the detector, and then combine it with your outer detector, which is this water veto detector I'm talking about. And then you can see that you can even drastically reduce this background a lot. And so your inner region becomes much bigger. So this is called self-shielding. Internal radioactivity is another problem. And oops, sorry. Okay, so this is another thing that we think about. So uranium, thorium, potassium, cesium, argon, I mean, there's just so many of them, right? These decays in the detector target, material surrounding the detector medium, the shielding itself, they're problematic as well. And so there's a number of methods that are employed to characterize the materials before using them in your detectors. And so in most cases, we're looking for less than 1 part per billion. So when I say that, I mean less than 1 part of uranium per billion parts of whatever the material is that I'm looking at. That's sort of less than that level is a level of radio purity that we're looking for in materials. So we have an arsenal of detectors that are designed just to characterize materials. The workhorse is probably this high purity germanium counting. And this is a picture of what it looks like from the outside at Snow Lab. But we also use things called like radon emanation. Okay, so that both of these, this is the detector for radon emanation. This is the computer system for taking the data and releasing it out. So essentially what you're doing is you're trying to trap a small amount of gas in this detector here. And so that's done using a mess of equipment. This is ICP-MS, another way of characterizing materials. This is a beta screener that's being developed at South Dakota School of Mines and Technology. This is the alpha counter that we have at my lab at SMU. And just to give you an idea, the real workhorse are these high purity germanium counters. Almost every component that goes into experiments gets counted by one of these types of machines. And there's essentially two types of systems that you can have. So essentially you commercially purchase a high purity germanium detector, but that's usually not good enough for your needs. And so you augment it by adding shielding around the detector itself. And then there's sort of a fully custom system that you can buy that's really expensive, where the cryostat and everything is designed paying strict attention to radio purity of the detector and of the system itself, so it can go even lower. And so just to kind of give you, this is like just sort of a sample, like just a standard size counter. This column here, the units are parts per billion. This column here is millibecquerel per kilogram, and the units are different because it means different things to different people. And then if you had a larger size sample, what you might be able to do. And so you can see that these custom systems, you know, they can do like a factor of 10 or 100 better in counting some of these radio impurities that we care about. Alpha surface screening, essentially here you put your sample into the bottom of a system, and then you look for alpha particles in the system. This is like it's almost like a wire chamber, but it's not wires, it's gas in it. And by using pulse shape discrimination, you can tell whether your alpha particle came from your sample or whether it came from the wall of the machine. And so this can measure alpha particles at the level of about 25 nanobecquerels per centimeter squared. So this is looking at surfaces, not volumes. And that's about where the surface or the instrument background is for that. If you wanted to do even better, eventually we need something like a beta cage. Again, an alpha counter. It's a wire chamber system, and it's in development. And there are lots of other options. So I'm not going to bore you by showing you pictures of every instrument that's out there. But the idea is that we really have a lot of instruments available. We do a lot of screening. The other thing that we do is modeling backgrounds. And so one of the model backgrounds that we want to model are sort of these alpha N interactions. Okay, and so there are essentially 3 software frameworks that exist that can calculate the spectra of neutrons that are produced by these types of interactions. Those frameworks are called sources, the USD web tool, and the newest one is NuCBot. All of these are software frameworks. So they take inputs from other software that does calculations. And so essentially there are 3 different libraries that can give you the cross-section inputs that you need to do the calculations. Empire, Tyndall, and Tallis. The Tyndall is a validated library, which can be somewhat trustworthy. And Empire is recommended by the International Atomic Energy Agency. But neither of them can properly calculate all the resonant behavior that is experimentally observed. So, it's sort of often doing comparisons between the two. Did I see somebody's hand raised? I know this is very detailed, but I just want to really impress upon you that this is a big part now of building the experiments that are going on, both the super CDMS, the Xenon 1 ton, which I know is now commissioning, and the LZ experiment. All of them, we're looking at a lot of this. So essentially, these tools just get you your neutron spectra that you then can put into JAMP4 to actually get your event rate out of. Yes.
Use machine learning in one of these?
No, these are just like calculators, essentially. I mean, very sophisticated calculators. All right. And so let me just show you, I would say, let's not worry too much about the fine details of this, but I just want to show you what the comparison between these different tools might look like to give you an idea. If you're really interested, you can go look at the paper to get all the nitty-gritty details, but these are comparisons of different materials used by different experiments using the USD web tool and sources for C. And so essentially, in the end, what you can see is that we found no major systematic differences between the two in terms of their input or output, their spectra, their yield, but both of them have cross-section errors. And some of their outputs, like to see these sorts of errors and problems, really require a human eye to catch. Similarly, there was a comparison done between NuCBot and Sources for C. NuCBot was used by the deep collaboration to predict their neutrons in the region of interest. And so I think the real take-home way here, though, is just taking from one example, their PMTs. So they found that NuCBot would give them 15 neutrons per year from the glass, and Sources for C said 13 neutrons per year from the neutron glass or from the PMT glass. And then the ceramic, which is part of the readout system, and other sorts of materials that just make up the PMT. So you can see the level of detail that goes into thinking about these is really a lot. So once you have all your spectra and stuff, of course, then you still have to plug it into your simulation tools. JAMP4 is primarily used. So here I use as an example the super CDMS geometry in JAMP4 because I can easily get my hands on it. And here's an example of sort of the output that comes from our JAMP simulations. So this is the event rate versus recoil energy. And this is in one of our detectors, just the raw output that you would get for spectra. And then once you have your JAMP simulation, you can do some analysis on it and produce some cuts. And you can see that we can reduce our backgrounds pretty well. This dotted spectra here would be like a 1 GeV WIMP. This spectra here would be like a 10 GeV WIMP. And in the corner here is sort of the different types of background classification that were used to produce the spectra. So then, we've been doing a lot of this. These two tables, like this is where you would get an F from your professor for putting something so unreadable on a slide. But the point is, the point here is this is from Super CDMS and from LZ. The point here is to say that we actually really track everything from screws. Like we put constraints on how much contamination we can have, how many impurities we can constrain, and we keep track of this at this level. All of this to just get, these are just the G2 experiments. Imagine what we're going to do when we get to generation 3. But yeah, these background inventories. And you shouldn't say anything bad about it because one of my jobs is to keep track of the Super CDMS background inventory. And then finally, as you might imagine, if the McMaster car copper is not going to work for you, you have to go and you search all avenues. It turns out you can't just buy it. When you can't just buy it, you build it. And so in some cases, you actually need copper made, specially made copper that is made through a process called electroforming. And when electroforming it above ground doesn't work, you make it underground. If you're in sort of a xenon-based experiment, whether it be xenon 1-ton or LZ, you make your own custom gas purification system because commercial xenon has 1 part per million to 10 parts per billion of krypton in it, and krypton is something you really don't want. So you have to build your own distillation column to get rid of the krypton. Similarly, in argon, you have argon-39 that can be really problematic. And even though you now have these underground sources of argon that you can use, still distillation can be really helpful. So when we can't find it, we build it. All right, and then finally, there are these neutrino backgrounds that are starting to become more important. It used to be called the neutrino blur. We now call it the neutrino fog. I think to indicate both that neutrino background becomes more important, it depends on what your detector target is, like at what level it becomes important. And also we like to use the word fog now instead of floor because the idea is that we would like to leave open the opportunity that we can get past it. And so essentially here, I think probably most people in this room have had this at some point, but basically you have solar PP neutrinos at low energies and high fluxes, and these can contribute to the electron recoiling background via neutrino electron scattering. And this happens at an event level of about 10 to 25 per ton-year at low energies. You also can get neutrino-induced nuclear recoils. And remember, nuclear recoils can't be distinguished, right? WIMPs, neutrinos, neutrons, they all look the same in your detector. And so in particular, it's this boron 8, which is this guy here, that we worry about most. This is the first one we're going to see in our detectors because it's the highest. This would be sort of on the order of 10 to the 3 events per ton year for heavy targets like xenon, argon. There's also going to be a contribution that we worry about at these higher mass WIMPs from atmospheric neutrinos and diffuse supernova neutrinos. And this is going to be at the level of 1 to 5 events per 100-ton year experiments. So another issue that we're going to have to deal with at some point in time, this probably is at generation 2, we're probably going to get, watch how clever I am, we're going to get a boron 8 solar neutrino signal for the first time ever in maybe liquid xenon and germanium. Which will be kind of nice because we know it's supposed to be there. And if we don't measure it, then we know we did something wrong. So there's putting a happy spin on background. All right, so let me summarize our direct detection needs. So what we need the ability to see low energy WIMP-induced nuclear recoils. And so these energies can be anywhere from less of 10 keVs to tens of keVs. So we need radiologically pure materials. We need the ability to measure low thresholds. We need the ability to distinguish nuclear recoils. We need the ability to mitigate radiogenic and cosmogenic backgrounds. And we need long exposures. So that means, and long-term stability. So if you have a long exposure, but your detector is not stable, that's also a mess. And this becomes really essential when you're doing modulation searches or diurnal searches. All right, so this is a good time to ask a question because we're about to move to a new topic.
Oh, great, thanks. Your bullet point about the difference between alphas and nuclear recoils. Can alpha particles like mimic nuclear recoils?
Yes, they can. Again, they can. And this is a much more of a problem for actually bubble chambers than it is in some of the other experiments, but they have a really great way to distinguish their alpha particles. It's actually really cool. And I'm not going to spoil it because we'll learn about it this evening. Other questions? Yes.
In the end of the day, how many events do you need to see to discriminate to a dark matter event?
Okay, so if you wanted to say how many events do I need to see, say, in my detector in sort of any given time, if I saw 5 events that I thought were dark matter events, you know, that would probably give you a 5 sigma discovery in most detectors for a win. Based on what I believe most experiments understand their backgrounds to be. I would do it. So essentially 1 event per sigma is my rough calculation. Now it obviously will have some finer details that different collaborations can give you, but if you're looking for a rough number, that's what I would say.
Now that you're mentioning the modulations again, I've got a question to that because you were mentioning the daily modulations.
Yes.
How, or maybe that's better to the end of the lecture.
No, actually, I'm not going to come back to talk. I'm not going to actually show any examples of the daily modulation detectors because I just don't have enough time. So now would be a good time to ask that.
So I was wondering, you said like for the annual modulation, we need about 1,000 events per year to actually measure this. How would we be able to see the daily modulation, or what does it? Is it more like a?
So what would the requirement be for the daily? So I think on an order of 10 events, if you saw an order of 10 events on order of 10 events coming from the direction, you know, of your win-win, I think you would be having a really strong case.
Okay. Would we also for the annual modulation have to take this into account, the daily modulation, because it changes my statistics also, I guess?
So I don't believe that they do, because they're really looking on a yearly cycle. They're not looking on a day, they're not looking at daily fluctuations. They're looking at event rates over the course of actually, you'll see in DOM, I mean, many years.
Yeah.
So yeah, so there I think the daily rate is not as important to them.
Okay.
Because they're just looking at events, not direction that they come from. Yes.
Yeah, just to follow up on that, I would have thought that the rotational rate is much slower, like than the orbital velocity. The rotational velocity is much slower than the orbital velocity. So I would expect you would need more events to discern the diurnal modulation.
But the diurnal modulation is about the direction that the events are coming in that you measure in your detector. And so if you have about 10 events that over the course of the day, remember the direction of your wind is different over the course of the day. But if you get about 10 events that seem to be coming from that direction, you're probably pretty good. What I would consider the problem with annual modulation is that there's nothing that tells you like this is a WIMP or this is some other particle, other than the fact that the rate fluctuates over a course of a year. And you have to match, that to the fluctuation. So you don't know if it's an electron recoil, you don't know if it's a recoil of nuclear recoil, you don't know if the recoil is coming from neutrinos from the sun or if it's coming from atmospheric. I mean, you have no idea what the source is when you're doing an annual modulation search. But when you're doing these sort of daily searches where the direction, you're requiring that dark matter particle, like you have to be able to measure the direction that it's going in. So that's why you need sort of the tracking. And you have to know that it's coming from the direction of your wind point. And so you reject everything else. That's why you can do better with fewer events that you measure in your detector. Because you still might have 1,000 events in your detector, but over the course of some period of time, but you only need like 10 of them to be coming from the right direction. For an annual modulation, you need thousands of events because you have to get that oscillation over a large period of time to match what you're expecting. So it's different because you have no discrimination. So the daily modulation, you have discrimination of what is a dark matter particle and what is not. Annual modulation, you do not, other than the fluctuation matches what goes on over the course of the year. So we're actually going to start talking about annual modulation in just a few seconds. So if there are more questions on that, maybe we can go a little further. Yes.
Yeah, no, so I just wanted to give another reference number for like sigma and
Yeah.
excessive events. So in dynamic technology, we actually have a near threshold excessive events, and it's 70 events, and
Yeah.
Sigma is 3.7.
Yeah.
And
So yeah, but Domic's a little bit different too, because primarily like in Domic, you're going after a lot lighter dark matter particles, right? And you're
I mean,
just,
it's a wind search, yeah.
yeah, and your discrimination is slightly different
It's
as well.
like below
Yeah.
10 GeV, but yeah.
Yeah.
It's,
Yeah, I am not actually going to talk about Domic. I apologize because I assume that Tang Yen is going to hit that in the next sub GeV dark matter lectures. So just so you know, it's not that I don't value Domic. I think Domic's a great experiment, but I also have a lack of time. But yeah, here I'm, was asked to mostly focus on the heavier dark matter. So,
right.
okay, so this is a great example. So what he's saying is that in Domic, to make a claim of a detection of a wind, they need something like 17 events. But again, it is a slightly different technology, and that's why I said this is, I can give you a rough idea, but it doesn't fit everybody. Yeah.
Actually, if I can just clarify, actually, we do observe an excess of 17 events,
Oh.
but we do not provide a definite interpretation for that. We do not say it's dark matter.
Okay.
Okay, so we will further investigate this, but
Okay.
we're not claiming it's dark matter.
Okay, so yeah, so my 1 event, 2, 3, 4, 5 event was kind of saying you can identify this as a nuclear recoil happening in your detector, and you have a good understanding of what your backgrounds are, like your predictive backgrounds. And that's not the situation that everyone is always in. So, I mean, if you had 17 events that you were certain were not background events, I'm pretty sure Dominic would be saying that there's, right, a dark matter signal.
Oh, I mean, that's exactly what we see.
Okay.
So we see like
Yeah.
an excess of 17 events, but.
And what did you expect to see? from
Yeah, we'll
backgrounds.
have to check.
Okay, yeah. So
On the
anyway.
order, I think of like 20 events and we see something more
Mhm.
like 40 probably.
Yeah.
But yeah, so I mean, this is what we see, but and we have investigated like multiple
Yeah,
systematic sources,
yeah.
but that does not
Yeah.
explain yet.
I mean, so this is also the other problem with dark matter experiments like that we have, is that there have been many times where people have seen more events than were expected. And so it always is checking and trying to say, what did you forget? And so to make a claim is kind of a big thing. So,
Right.
all right, yes.
So from a detector's point of view, what factors can affect the long-term stability? Because if you don't touch it and if there are no earthquakes, you just let it sit there. So what can screw up?
Sorry, the mu one, I didn't, can you say the question one more time?
So the last point about long
Yeah.
movements is long-term stability.
Yeah.
So if you don't screw around with the detector, you just let it sit
Yeah.
there, right? So can go wrong.
Yeah, so many things can go wrong. You're right? This is why you hope that your detector will be stable and you try to keep it as stable as possible. And then when you make changes, you record it. Oh, or are you asking what types of things can go wrong?
Yeah, what kind of
Oh
things
my
can
God.
go wrong?
Everything. You could have, I don't know, some kind of leak or something happen and you have to warm up your whole experiment and cool it back down. You could have failures of different types of components. I mean, like, if you can imagine it, it can go wrong.
Oh, okay.
Yeah, and I mean, and some of these experiments are really quite sensitive. So yeah, I mean, just you could have a component fail, you could have, I don't know. You could have the environment that you're in. For some reason, it could just become more noisy, meaning that for some reason, more events like, you're operating in laboratories, maybe some new experiment comes in and produces some set of noise, a new set of like electric feedback of some sort or noise that then raises your noise threshold. Yeah, there's just sort of lots of things that can happen.
I was thinking more along the lines of like germanium crystals or whatever, right? They are chemically stable, I guess.
Yeah, that when I talk about stability, I'm really talking about everything you need to read out the experiment, to support the experiment, those sorts of things. Like, yeah, I mean, the detector itself isn't going to be unstable. It's the experiment that can be unstable in the sense that things could go wrong that end up where you have to change your settings or you have to change your thresholds. And you just don't want to be doing that often. You'd prefer that you make your settings, you hit the go button, and you just sit back and relax. Right. All right. Direct detection experiments. So the search space. There is no, there is no lack of different types of theoretical models for WIMPs. This is just a sampling of different types of classifications. You can see that it spans a pretty large WIMP mass range. So we have WIMP mass versus the WIMP nucleon cross-section in centimeters squared. All of these are always going to be assuming from here on out a spin-independent interaction with the nucleus unless otherwise specified. And so this is in centimeters squared, or if you like picobarns better, that side converts it to picobarns for you quickly. So let me just show you the answer right away. This is currently where we sit as a community and what we've excluded from ideas of dark matter, our dark matter particle being, coming from supersymmetry. And so at sort of the highest masses, the liquid noble experiments tend to provide the best sensitivity. And at these lower masses, more of your solid state experiments and things like DOMIC, CREST, super CDMS, they tend to provide the best sensitivity. So the goal is to move down. So we want to move down this way, and we also want to move out this way because there's a lot of space over here that is still open. And then, of course, we have this neutrino fog, this neutrino background that's coming that will provide a challenge. The current experiments that are being commissioned and deployed essentially should get down to this neutrino background. And then the generation 3 experiments are the ones that either will bridge the gap if there's a little bit left, and perhaps go beyond the neutrino fog if we can figure out a way to make that happen. So I think the first thing you have to do when you start talking about direct detection experiments that are searching for dark matter is address the question of, did we already see a signal? And so I think probably everyone in this room knows that the DAMA-Libra collaboration have been reporting positive results of a dark matter signal since 1998. And DAMA was a 100 kilogram sodium iodide array that operated in the Gran Sasso lab from 1996 to 2002. And Libra was an upgrade to a 250 kilogram array, still sodium iodide crystals, and it's been operating since 2003. They presented their first results in 2008. This experiment measures scintillation interactions from particles. So scintillation from particle interactions. Sorry, I'm mixing up my words. They have no discrimination between nuclear recoils and electron recoils. So you couldn't say if when they are recording an event, you don't know if that's a background event or if it's a background event. But what they try to take advantage is that of taking lots of events is, do they see that modulation over the course of a year that you would expect from going with the whip wind to going against the whip wind and back. And as you can see, they clearly have observed a signal of something over 14 cycles. And so that signal now has a confidence level of 12.9 sigma in the 2 to 6 keV bin. So again, I mean, I already said this, no background discrimination. So in the physics community, there's a debate over whether this is a background or it's dark matter, that is some interpretation of dark matter. And I mean, it's complicated and it's hard because there are disagreements even on the background models. And so these are just some examples of some of the disagreements, or what could it be. So you can actually get 3 keV X-rays and Auger electrons that are associated with this rare electron capture that happens when potassium decays. And so it could be, you know, it was thought at one time, and there's actually a paper out there that says this explains at least the amplitude of that modulation if you take this into account again. Radioactive argon from impurities in a nitrogen purge could be possibly a problem. Radon included neutron or gamma ray flux from the cavern itself. These are all sorts of issues that are up there. So, you know, what is it? I can tell you that I honestly don't know. Go ahead.
Are there other things that we know that fluctuate as the Earth moves around the sun?
Yeah, so like the muon flux actually modulates, but that's been looked into and it seems not to be something that can be explained. The issue here is actually, let me kind of move over to this slide, is that, you know, it's been an ongoing issue for a very long time and people don't understand it. It's one experiment that sees it, and every other experiment has not seen dark matter that seems, I mean, hasn't seen any signal in their detector. And it seems like some other material should have, or experiment, right? Some other target should have been able to see it by now. It can't be that dark matter, well, maybe it can be. It'd be really unusual if dark matter only interacts in sodium iodide crystals. Like, you have to ask yourself why. And there have been lots of different explanations proposed over the years that haven't panned out. Channeling of the particle in the detector at one time is actually, so you can imagine that, like, the particle channels between the lattice. That was something that was explored a long time ago, but I'm just thinking of all the ideas that people have come up with. So I would say this has certainly perplexed theorists and experimentalists. So now there is sort of a worldwide effort of a number of experiments that are trying to validate or figure out what this experiment is. What is a signal? Is it some kind of background that we can characterize? Is it really genuinely that we have seen dark matter for all these years and it's just so unusual that we haven't been clever enough to explain it yet? And so those, so you have still DAMA Libra, but also in Gran Sasso, you have, I think it's Picolon. You have the Kim's plus the DM ICE collaboration have joined together to produce the cosine 100 experiment that's happening in the Yang Yang. Actually, Picolon is in Kamioka, the Yang ICE experiment in Confront. There's a lot of efforts out there. The issue is the hardest challenge for people trying to replicate the DAMA experiment is finding a sodium iodide crystal that is radio pure enough. So I think that is actually a nice punch point to the fact that we just spent like an hour talking about backgrounds. Is that the challenge here to being able to reproduce it is getting a crystal that is pure enough to be able to help, to get to the sensitivity that DAMA Libra has. Yes.
I have a question on the 12.9 sigma. Like, what is this with respect to? Because if there's no background, what is the concept of like an outlier event?
I mean, I guess this 12.9 sigma is, the fact is that it's modulating, right? Versus you see no modulation signal.
Yeah, but like, what is it a sigma of? Like, is it bits? Is it like a?
Yes, so it's a fit over a period of time. And so like essentially the longer they take data and see the modulation, the bigger their sigma grows.
But the production process of the crystal are not available for.
Yes,
another
okay, so
experiment?
this is something that I was discussing before here with one of the other students in the class, is that I have never had a very satisfying explanation of why it is that you can't just go to the same company that DAMA Libra has and buy the same quality crystal. We just have to accept the fact that people have tried and they haven't been able to do it. And so what they've had to do is resort to growing their own crystals and coming up with their own formula. And so at the BES Institute in Korea, they're actually growing crystals and working on this. Also, Frank Calaprice at Princeton has been working with a company to try to essentially get powders that are clear enough to develop the crystals from. So I think, at this point, we can't worry about why can't you just do this and enforcing that when it's not working well. And so people are doing what they can, which is going out and getting their, trying to develop their own crystal growing, operations at the level. Yes.
So have you heard about these possible explanation for the DAMA signal that is related to the fact that their noise is like increasing during the year, but they subtract like the average value, and that might actually lead to this motivation?
Yeah, I had, yeah. So the question was, did I hear that that there's this idea out there that DAMA's noise increases over the course of the year, and so they subtract off like the average of the noise, and this somehow could produce the fluctuation. I hadn't heard that exact explanation, but if you want my personal opinion, I really think it's a background that hasn't yet been identified. I believe that DAMA Libra, that they're competent scientists, they're seeing something. The question is, what exactly is it? And that's what we all want to know. And it's been a long time trying to figure out what it is. And it can be a quite heated debate in the community. It can be quite heated. So
Right. So I guess I wonder what's your personal opinion on the fact that they haven't really disclosed or like their analysis pipeline. And
I think at this point, like, we can't force people to cooperate in the way we always want them to cooperate. We in CDMS have been accused by people of sitting on our own data and not giving them it in the form that they want at the time they want. And, and so I don't want to be too critical of a collaboration that's being protected, because sometimes there's good reasons that they don't do that. I think what we have to do is we just have to accept where we are rather than wishing what we could have, say, what do we have and what can we do? And what we can do is we can try to replicate the experiment. And so that's what we're doing. And that's my own personal feeling in it. At some point, you can wish all you want, force all you want, but sometimes you just have to live with what is the reality of the situation. But actually going on that, let's talk about cosine a little bit. So this will be, yes, I understand. I see the clock. I think we're going to end pretty well on time. Cosine is located in the Yang Yang laboratory in South Korea, and they put out results not so long ago. They have, this is, their pictures are so pretty. But you can see how clean everything is, right? 8 copper encapsulated sodium iodide or tellurium crystals. So 106 kilograms in total. They had 2 3-inch PMTs per crystal. Their trigger was essentially at a 0.2 photoelectron threshold. And they have calibration sources that they can insert through tubes. This is quite typical. We've done this too in CDMS. And their total background, okay, so this is again where I'm talking about the crystal background here. So their total background is 2 to 4 times the Dama Libra average for their crystals. And so this is like 2.7 counts per day per kilogram per KE. So this is counts per day. And that's in their 2 to 6 KeV region. This is the region of interest. This is the energy region that Dama Libra sees their signal. Their uranium, thorium, and potassium are below Dama, so that's good. And their PMTs have very high light yield. All right, and so these are sort of some results. These are energy spectra that you're looking at here between 2 and 20 keV, and the signal efficiency for each of the crystals that they use. And their signal efficiency is measured using a cobalt source, which produces neutrons. This here is showing rise time. So essentially, all of this looks good. So they had 1.7 years of exposure. So this is like 97.7 kilogram days. They did a global fit using cosmogenic and sinusoidal components simultaneously for each of the crystals. They excluded crystals 1, 5, and 8 in their analysis because they had excess PMT noise. And so, you know, that didn't help them the analysis. Their sideband, so the idea is they do a blind analysis. And so the region just outside the blinded region, that's what a sideband is. It decreases exponentially. It agrees with all the known cosmogenic components. So it really seemed like things were going good for them as far as their understanding of their detectors. And this is their results from their paper. So they had a best fit amplitude and phase in the 2 to 6 keV region. You can see it right here is this black dot. This is the Dama Libra best fit. Okay, if you were to map them on top. So the amplitude is 0.0092 plus or minus some fraction counts per day per kilogram per keV. So this is the amplitude of the oscillation above what is predicted. And this is the phase of when, you know, when the sinusoidal goes up and down. So the issue here is that the result is consistent both with the null hypothesis and Dama Libra's best fit value. So again, we have no answers. But on more of a positive note, thinking where we're going, or where this experiment's going in the future, they expect 3 sigma coverage of the Dama region within 5 years of data. And once they're able to cover 3 sigma of the region, we should at least have a good hint of what is going on. And so they have some ideas how to advance things in the future. And so, look how I ended on perfectly on time. I'm 1 minute early. So this afternoon, we'll pick up with the liquid noble experiments and talk about the rest. So thank you very much.